Kia ora koutou, Reese from QuickSense here, and today we're looking at the angle at the center of the circle. Now, another way of talking about this angle, or this theorem, is what's known as the inscribed angle theorem. Inscribed angle theorem. And that says that the angle at the center of the circle, so if we have something like this, okay, now I'm going to do a little bit of freehand. So we've got 3 points on the circumference, and we've got an angle here and an angle here. So this one here, the angle at the center of the circle, is twice the size of the angle at the outside of the circle, right? The circumference, but they're both C. So C here is equal to 2 lots of the outside, 2O. So how can I use this to help me answer the question here? Well, immediately I can see I've got a triangle here, and because this is an isosceles triangle, these are the same. So that tells me what this angle is, right, at the center, because I have the angle at the outside as well, which is what my x is. 45 plus 45 is 90. Angles in a triangle is 180, so this must be 180. And if this angle is twice the size of the one at the outside, the value of x is half of that, which is 90. So x equals 90 degrees. In this next question, we're going to have to do a classic geometry question breakdown where at the end it will look perhaps straightforward, but it's not always easy to see where we need to begin. So looking at this, I need to somehow find out what x is. And it's really not obvious where we should begin. But I can see this angle here and this angle here. And actually this angle here is the angle at the center of the circle. So what I'm going to look for is there this kind of shape, right? Well, there is, but it's not obvious, because what's happened is I've moved this line here over so that this point means that this is the diameter, right? So what does that look like? Well, it looks like the center. It looks like that, right? So this is the angle in the center, and this over here is the angle at the outer, at the edge. So 80 in here is twice of this angle here, which is 40. So let's write that down. The angle ABD is equal to half of angle AOE because of the inscribed angle theorem. All right, so what else can we do here? Well, this is going to be, we can probably fill this in, right? This is going to be 100. And because this is an isosceles, this is also 40. This may not be helpful, but we're just going to build up a sense of this space here. Now, what I really want is this angle in here, right? Because as you can see, well, maybe you can, right? We've got this system here where we've got D, I'm going to exaggerate it here so you can see it, D to C, and then A is over here, and B is over here. Okay, so I've got this shape here. It's not easy to see on there, but these two angles here are the same. Okay, so those angles there are the same. And they're the same because as I move one across, right, let's think about if I were to move B around to C, right, this line here would exactly match up with this line, and this line will get shorter and shorter and shorter until it lines up with this line. So, the angle ABD is equal to the angle ACD, which is also x, right? But we don't have that because currently it's 40 plus something. So to find that, luckily, I have this position here where this point is meeting at a right angle. Okay, and how do I know that? Well, because this here is the diameter, and then moving from the diameter, the chord will always meet at a right angle. Right, so as I move along, it's meeting at a right angle. So because BE is the diameter, okay, so because BE is the diameter, it goes through the center, angle BDE is equal to 90 degrees. And if that's 90 degrees, that's 60 degrees, 150. This angle here must be 50 degrees. Oh, sorry. 150 must be 30 degrees. Right, so now we have this situation here, where 40 and 30 is equal to ABD. So 40 plus 30, we're getting ahead of ourselves, is equal to ACD, which is equal to x. 40 plus 30 is 70. Therefore, x is equal to 70 degrees.